a lot of these structures in civil engineering, there are so many and they have to be so big that in that direction they turn out to be expensive. You get the big things and you put them in place if the material is cheap. In antiquity, it was the dried mud. In Roman Empire times, it was the fired brick. That was a more expensive kind of mud. And then in the 1800s is when iron bridges started to spread on the landscape. Taller buildings came with them all the way to the skyscrapers of New York City originally. In fact, I think I'm wrong. The first skyscraper, I think it was in Cincinnati. It's worth investing, or Columbus, one of those cities from the Midwest. The point is the following: bigger things require bigger cantilever components, and they come out of the invention of cheaper versions of what I just showed you. And the much cheaper material is the concrete. Again, from the Roman times, concrete. The problem with concrete is that if you make a beam out of concrete, we'll sketch it here, and then you place it in bending. Yes, the upper fiber will be in tension, and it will fail when its maximum allowable stress is reached. So the SMA here in tension is when the beam will snap over its backside. Actually, in this shape, it will snap here first. I told you, you get out on the balcony of an old building and you'll see that under your feet, this is the floor of the balcony, there's a crack right here. The balcony did not fall to the ground because of the story I'm telling you. The maximum allowable stress on the belly is for compression. And the thing to know about concrete, imagine even a brick. You can't put a brick in bending because each of us is too feeble, but the concrete is much stronger or resistive in compression than in tension. And that means that, okay, I'll write this: SMA compression is greater than SMA tension. Amazing. So, but now the builders of these structures, I mentioned skyscrapers, but pretty much everything else today, know these things. And for that reason, they designed the cross-section of this beam to contain two materials. To contain the concrete, let's do the concrete, sketch it this way, and reinforce it with steel rods. Steel rods that run longitudinally in the close vicinity of the upper surface. Here are the steel rods. You've heard of the expression steel reinforced concrete? Well, it comes from here, except that the reinforcing is distributed intelligently through the cross-section. It is placed to become, for the steel to become the fiber that carries the most of the tensile stresses. And this drawing comes with its own infinity of freedom, because you can have these rods positioned in that vicinity in all sorts of ways. You can have more of them closer to the upper surface, fewer not so close, thick ones where it matters, thinner where it matters less. In other words, if you want to do a thesis on today's version of this idea of evolutionary design, you can impress people with a drawing that has a huge number of these circles in the cross section, circles that become smaller in diameter and less numerous as they migrate slightly away from the upper boundary of the cross section. And by the same token, if you want to get closer to the boundary, you have to implant thinner circles closer to the boundary to avoid cracks in the concrete and whatever. These people, they know much better what kills a good idea. So you see, steel, the material, and concrete together, people call it a bi-material. Don't buy that sort of language. The so-called two-component material has a drawing. It matters where you put this metal and where you put the concrete. A bi-material is not an alloy. It is a drawing, it is a design. Just like the muscle, it comes with a bone. And the bone is inside the muscle. And that, if you make a cross-section through it, that is a drawing. I tell you this because in this world, the drawing is not respected. It's not even taken for granted. Because it smacks of engineering. That is what's being taken for granted in science. That direction is traced by these problems that you're solving right now. And that's why I call this thing, I didn't say stairway to something in the beginning of the course, didn't I? I think I did. No? I forgot to say it?
You said stairway.
I did, yeah, okay. I was still dreaming when I started my lecture. The problem that we solved until the last time, 10.2, was about the lightest structure that was shaped this way. Shaped with a junction here which allowed for free rotation, meaning zero torque, and for the lightest version of this thing, while keeping the loading fixed, meaning least material version of this, you concluded that the best is the one where let's call it the torso above the legs is absent. So the V or the Greek lambda is the way. Well, if this is the way, then it is worth repeating. And then you discovered why iron bridges and trusses look this way. Everything around the Eiffel Tower, inside of it is this way. For this reason. Okay? There's a whole aspect of the history of engineering, people trying to figure out what the great engineer Eiffel was thinking when he designed his structure. The most famous structure is the Eiffel Tower, but also the skeleton of the Statue of Liberty. He designed that. And why that skeleton looks this way. And Eiffel left very few hints about the way he was thinking, because he was a businessman. He didn't want to be copied and put out of business. And it turned out that his mantra was find the piece of metal that is not stressed and eliminate it. Simply get rid of it. And that's how I use this idea too, the way I was teaching this course. That is the way to arrive at the shaping and at providing internal structure. All right, so that was one problem. The next problem set, which is set number 7, consists of problem 1012, which is due on Monday, the 24th of this month. Wow. This is the other problem, the sister problem of the first. It's the same problem except that the junction doesn't allow free rotation, and so you have that this way, with the assumption on top that each of these 3 bars in compression are slender enough to fail when they buckle. Remember now, you don't remember, maybe you do, you have a column in compression. If the force P is great enough, then suddenly it's just like the leaf or the old branch that becomes limp, it buckles. Yeah. I'll share with you a very common joke when I was growing up. So here's your friend. That's his foot here. And he's here. And not suspecting that you're a joker. And you come from behind. So he's looking that way. And you push the back of his knee. And then he buckles. He doesn't know why, but he simply, sometimes it really works. But but this is the beginning of this problem. Meaning problem 10.12. So now you have a three-part structure supporting a weight. First through a trunk and then through 2 legs. And the question is, at what, again, going back to the lightest, smallest volume, what is the structure that's strong enough to hold P without buckling and but with minimal volume? And it is covered. That it is the structure that if the height is h, then the torso should be approximately 0.6 of h. Just like in the case of my friend. From top to the pelvis is 0.6, and then the legs are 0.4. Yes, and of course you know why now the members of these animals, from all of them except the fish, have this aspect of design, which is to deal with buckling in a reversible manner. An attic with the top of actually, imagine if one of these pictures from a history book, the facade of a temple. It's a heavy thing. It's made out of heavy stone. and it is supported by columns. Relatively few columns. Did you ever ask why? I'm still asking. Obviously, I dealt with it in the book, but not as seriously as today. So here's one, here's another, and they're supporting what? They're supporting the weight of this beam that's horizontal. Forget about the attic shape. Think of it as a beam this way. And then, of course, you can look at 3 and approximate it as the 3-time repetition of 1. Here's the 1. The 1 is the one, this one, namely, here it is, the beam here supporting a weight. The weight would sag. I'm exaggerating the thicknesses of these parts of the skeleton, but the horizontal beam is like the first part of today's lecture. The vertical column is like what I was joking here. And so that's actually the design, okay? So the sagging would be this way. The beam, the column would be thick enough to avoid the buckling. See that? But buried in this drawing is the easy number called n equals 3, which is the number of columns that I thought of. Why not 10? There are all sorts of people who think that goodness comes from distributing things uniformly on the landscape. Yeah, why not make the facade look like a picket fence? Many, narrow, skinny, each carrying a small fraction of the weight, therefore skinny, yes, able to do the job, not buckling. Yeah, why not? You know, the answer is that this is wrong, because you look in the forest and you don't see, things standing up, call them trees, that are identical to their neighbors. You don't. Meaning the nature is contradicting you everywhere you look. And in a future problem, you'll see why. It has to do with the fact that to support this weight, with the requirement that the supports do not buckle, the few, or the one in this case, is the answer, not the many. In other words, not this, this instead of the same image with many small supports. Meaning this one is lighter than this one. And that's kind of counterintuitive. But the answer comes from questioning yourself and being free enough in mind to think that you and your intuition may be wrong. See that? Okay. I think that this is a good place to call it quits. In the next, for the time being, in the next lecture we'll have a taste of what happens in the forest, about that kind of design, which is slightly more complicated. It is, you say columnar, built of columns, vertical columns. Parts of those are implanted in the ground. But those things in the forest are also blown from the side by the wind. meaning they're in bending, and that is why that topic belongs in this chapter. And less known to people is that everything that grows on land, on earth, is pumping water from the ground to the dry wind. You see that? You've heard the expression that the trees like water? Yeah, of course, forget about that. The water likes the trees because that's how the water flows upward against gravity. Or you also know, you may have heard that animals like vegetation. I told you already, animals are water trucks, so they go to where the water is, and never mind the trees. They go there, and then when they die, they leave you there. Don't be so sad. Okay, I'll see you next time. Make sure that you keep yourself in shape so that you join me on Wednesday.